Okay, so like I said, every lecture is going to be put online, okay? So you can do that as well. All right. Start out, let's talk about solutions. A solution is a homogeneous mixture, all right? It's going to be made up of a solute, bless you, and a solvent. The solute is what is being dissolved. And the solvent is doing the dissolving. Basically, here in AP, for the most part, let me close my mail. For the most part, our solvent's going to be water, almost exclusively. And if it is water, then we call it an aqueous solution. Aqueous, of course, dissolved in water. This is still awesome. Okay. So then you'll be up next period as well? Yeah. Okay. Perfect. Okay, if something dissolves in water, it's either an electrolyte or a non-electrolyte. If it doesn't dissolve in water, then it's neither. Okay? Both electrolytes and non-electrolytes have to dissolve in water. So we have electrolytes, which electrolytes allow the solution to conduct electricity. So the example given there is sodium chloride. When you throw sodium chloride in water, the sodium chloride allows for the transfer of charges, and that'll light up a light bulb. If it doesn't, it's considered a non-electrolyte, but it still dissolves. So a great example of this is sugar. We'll learn a little more general idea of what it is. But we know that, especially if the water is a little bit warm, sugar will dissolve in water. So here are three examples. We have pure water. We have sucrose right there. And then we have sodium chloride. So sucrose is not going to light up the light bulb. Sodium chloride is going to light up the light bulb. So there's two different types of compounds that we can throw into water. There are ionic compounds. And what type of elements make up an ionic compound? A metal and a what? Non-metal. And really, we'll learn later on, sort of a better idea is to say a small atom plus a big atom. But basically, a positive ion and a negative ion. Anybody recall what the positive ion is called? Cation, yeah. So the positive ion is the cation. And the negative ion is the anion. So when we throw an ionic compound in water, and this is true for any ionic compound, it's going to dissolve. So even the ionic compounds that we say are insoluble, they still dissolve, just not a whole lot. And when they dissolve, they dissociate. And to dissociate just means to break apart. If you break up with someone, you dissociate from them. Then they go on to date your brother because they don't care about you or your feelings. It's okay. It's okay. Family reunions are pretty tough, but it's either perfect little family or perfect little kids. I just hate them. Okay, so when they dissociate, they are no longer this arrangement of ions. They're no longer this three-dimensional structure of ions. They are now free-floating ions. Okay, and we have some examples down here. So let's look at these examples. So when I take sodium chloride, solid, and I throw it into water. So remember that's called a yield symbol there. If I write H2O over the yield symbol, that means that I'm putting it in water. Now when I do that, since it's an ionic compound, it breaks up into its ions, which is why it's very important to know the ions. So this is going to break up into the sodium ion and the chloride ion. So there it dissociates. Another one here that I gave you as an example is sodium sulfate. When I do the same thing, when I throw that in water, now we're going to get 2 sodium ions. And again, it's important to know the ions because what I get often from a very small portion of us, but what I get often is this done incorrectly. So here's going to be the wrong way to do it. The wrong way is for the sodium sulfate. Some people will write this. Okay? They won't break it up into the sodium ion. They'll try to make a brand new ion. And again, that's wrong. Okay, you got to know what the ions are that it breaks up into. It breaks up into the sodium ion. What is the sodium ion? It's an Na+. That's what a sodium ion is. When it breaks up into those ions, it is the ions that conduct the electricity. It's a bad idea to think of the ions as carrying the electrons from one electrode to another. It's the ions themselves that conduct the electricity. All right, so what happens is the ions become what are called solvated, which basically means that they are surrounded by water molecules. And I know that you may not remember all of this, but let's take a look at a water molecule here real quick. So there's a water molecule. All right. The oxygen is very electronegative, which means that it really, really attracts the electrons. The hydrogens are not very electronegative, which means that it doesn't very much attract the electrons, which we end up with what's called a polar molecule. And we'll explore this in more detail, I think, in chapter 8 or 9. But I just want to mention it now. So we get this polar molecule, which means that basically there's a negative portion. The oxygen is slightly negative, and the hydrogens are slightly positive. So we end up with this negative and positive portion of the molecule, and that negative and positive portion of the molecule then attracts certain ions. So, let's use red here. A negative ion is going to be attracted to the positive portion, And a positive ion is going to be attracted to the negative portion. And let me take this picture here and zoom in a little bit. Zooming, 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 zooming. As good as she gets. Take a look. Here's the sodium. Look at this one right here. Right? So here's the sodium. That's a positive ion. That purple sphere there, that's a positive ion. And then all of those reds, those are the oxygen. We said that you can't see it, but we said that the oxygen is the negative end. So all the negative end is surrounding that positive ion. Why? Opposites attract. Right? Opposites attract. Here, this is the negative chloride, and now the hydrogens are all surrounding it because, again, opposites attract. So that's what happens in the solvation process. The molecules will literally surround the ion and rip it away. As long as it has enough energy. If it doesn't have enough energy, it won't do that. And that's how we end up with precipitates. That's how we end up when I throw an ionic compound in the water and it doesn't dissociate completely. It just breaks up just a little bit. All right. We have space. Let me use this space right here on top of page 36 because I think, let me look real quick. I think I want to talk to you about, oh no, I guess we'll hit them next. That example. Yeah, we'll hit it next. So that's ionic compounds in water. All right, so in other words, if it's made up of ions, that's how it dissociates. If it's not made up of ions, if it's a molecular compound, which molecular compounds are only going to be what type of elements? Yeah, just nonmetals. They are typically carbons and hydrogens. Okay? So here you can sort of see that CH3OH, that's just carbons and hydrogens, and you have the extra oxygen in there. So that's a covalent or molecular compound. Some of them dissolve in water, and the ones that dissolve in water are the ones that are really polar. So let's just make a note here. Only polar molecular compounds dissolve in water. So if I have something like, let's say pentane, which is a C5H12, that's going to be nonpolar. And again, we'll get into polar and nonpolar later on. I'm just letting you know that's nonpolar. So that's not going to dissolve in water. So since that's nonpolar, it does not dissolve in water. So it's not an electrolyte or non-electrolyte at all. Right? It's neither, because an electrolyte and a non-electrolyte dissolves in water. Well, pentane doesn't dissolve in water. So when these molecular compounds dissolve in water, they're not made up of ions. Right? And that's important to note. They're not made up of ions. Since they're not made up of ions, we can't break them up into ions. Right? Like if I were to, let's say, just like hack you apart, like cut you up real viciously, right? I wouldn't have dog parts, right? I'd have human parts in my backyard buried. But because you're not made up of dog, right? A molecular compound is not made up of ions, so when we break it up, it won't break up into ions. And that makes sense, but you got to remember that. So what I often like to say is just those molecular compounds, they just get wet. Right? When we dissolve them in water, all they do is get wet. So here's an example of methanol, CH3OH, and you can see the water is still surrounding it. I mean, it's still mixed between it, but it's not really broken up at all. It stays together. That CH3OH stays together. Now this is a polar compound, so a polar compound does dissolve in water. Okay, so that's electrolytes versus non-electrolytes. Electrolytes dissolve, break up into ions. Non-electrolytes dissolve, do not break up into ions. Okay, so let's just jot that down real quick. Now, when we throw that methanol in water, right? So, go back. Let's talk about the ionic compound real quick. This will be a review, and again, we'll cover all this stuff later on as well. But when we throw that ionic compound in water, we're breaking ionic bonds, right? So the sodium and the chloride are held together in a strong ionic bond. Throw it in water, we break that ionic bond. Methanol is methanol, which is CH3OH. That's the molecular compound, so it's covalent. Is it held together with ionic bonds? No, right? Because there are no ions. What is holding those methanol molecules together? Anybody remember? It does have hydrogen bonds. What's the broad category for hydrogen bonds? London dispersion force is another type of. There. What? That's another type of these intermolecular forces. Right. So intermolecular forces are, here's a molecule, and there's a force of attraction holding them together. That's an intermolecular force. Okay? It's between two completely different molecules. And so the methanol has that before we throw it into water. Right? A methanol is attracted to another methanol. That's an intermolecular force, a force between two or more different molecules. They're really weak, so we don't call them bonds. Right? Covalent bond is pretty strong. Ionic bond is pretty strong, especially compared to those other forces of attraction. But the ionic bond and the covalent bond are still just forces of attraction. They're just really, really, really strong forces of attraction. So we have this methanol that has these intermolecular forces, and the water has to break those intermolecular forces in order for the methanol to dissolve. A better example to talk about this is, let's say, glucose. So here are two different glucose molecules, right? So here's the glucose molecule, here's the glucose molecule. They have a bunch of hydroxyls, OHs on them, a bunch of them, and those all have hydrogen bonding. So those all have that really strong intermolecular force. So an intermolecular force is holding these two molecules together, right? That's why it's a crystal. It's a crystal because we have these strong forces of attraction that are holding each other. So the molecules, when we put them in water, the water is strong enough to break apart the intermolecular forces, so the molecules go on their separate way. The molecule itself doesn't break up. The molecule stays put together. What breaks up is two different molecules. Okay? Yes. Yeah, that strong force of attraction between the water and this molecule is why they break apart from each other. Right? If it was a strong force of attraction, if it was stronger than that, then they wouldn't break apart and end up marrying your brother. Because you would have that strong force of attraction. But you don't. It's just fake. Yeah, that's exactly what we're talking about. Again, we'll talk about later on, like dissolves like. A polar molecule, so we know water is polar, will dissolve other polar molecules because they have similar forces of attraction. Okay? And again, we'll talk about all that later on. And I imagine now the seniors are like, man, 2 years is a long time. Right? And that's fine. We'll get you there, man. We'll get you there. All right. So we talked about electrolytes, non-electrolytes. Let's talk about electrolytes again, because we can break electrolytes into strong and weak electrolytes. And this is how we're gonna break up strong and weak electrolytes. Okay? A strong electrolyte we're going to make a couple different statements here. This is going to be an ionic compound that is soluble. So that's going to be a soluble ionic compound. It used to be in AP that you had to memorize the solubility chart. Like it would say nitrates are always soluble, this is always soluble, that's always soluble. We used to have to memorize that. AP has done away with that. They say you don't have to memorize the solubility chart. There are just certain ones you have to memorize. So these are the ones that you have to memorize. If it has one of these ions in it, it's soluble. Okay? So these are things that are always soluble. We're going to say group 1 metals. So like if it has a sodium ion in it, a lithium ion in it, a potassium ion, any of those group 1 metals, it's 100% soluble. Nitrates. So anything that has a nitrate in it, which the nitrate is the NO3 -1. That's the polyatomic ion. You're gonna have don't forget you got a quiz on those on Monday. And then acetates, which the acetate is C2H3O2 with a -1. And then the ammonium ion. Oh, sorry. Let me write the name. Follow the pattern. Which the ammonium ion is NH4+. So these, if an ionic compound has these in it, it's soluble. Which means that it's a strong electrolyte, which means that it dissociates completely. Those are the 4 sets that you have to memorize. Group 1 metals, nitrates, acetates, the ammonium ion. Everything else then is a weak electrolyte. So weak electrolytes are insoluble ionic compounds. And like I said, it's basically anything that's not in this group. Now, if it gives you a solubility chart, then realize that anything soluble dissociates completely, anything insoluble does not dissociate completely, and we'll review that here in a second as well. All right. So let's talk about, let's just talk about strong and weak electrolytes here. If they conduct electricity very, very well, it's a strong electrolyte, and they exist mostly as ions. We use the single arrow for the yield symbol, and that indicates we have almost entirely just the products. In some cases, we do have just the products, so we say that the reaction goes all the way to completion if there's a one-way arrow there. So, for instance, here with the sodium chloride, I only have the sodium ion and the chloride ion. Okay, and if it's a strong electrolyte, and again, these guys, strong electrolytes. We'll talk about strong acids, strong bases in the second semester, so we're not too worried about that right now. Weak electrolytes are your insoluble ionic compounds. It has to break up into ions in order for it to be an electrolyte. All right, if it doesn't break up into ions, then it cannot be an electrolyte. For these substances, they are slightly soluble. We call them insoluble, but really we mean slightly soluble. And then we're going to have an equilibrium symbol. So instead of the one-way yield symbol, we're going to have the two-way yield symbol. What that means is we have some of the left and some of the right all the time. Right? A little bit of the molecule is there. Remember, the molecule itself can't conduct electricity. Like sodium chloride, if sodium chloride stayed together, it wouldn't conduct electricity. But it doesn't stay together, it breaks apart. So the molecule itself does not conduct electricity. It's the ions that conduct electricity. So if I have mainly the molecule here, just a little bit of the ions, does it then make sense that the light bulb is dim? There's just not that many things there to conduct the electricity. Right? Just think if we had to, for some reason, take bags of sand from the door and throw them by the window. Right? And two of you were doing that. But the rest of us just sort of sitting around watching you do it. Now, that would be a weak electrolyte. There's only a couple people that are actually transferring that charge over. Right? A strong electrolyte, now everybody's doing it. Right? So we're going to get that charge, we're going to get those sandbags over there much, much quicker because there's more of us able to do it. And that's why a strong electrolyte is going to be a bright light bulb. A weak electrolyte is going to be a dim light bulb. Right? So let me show you an example, and then I'm going to be done here. That's about as much as I want to talk today. So let me show you an example of a strong electrolyte. So again, this is going to be any soluble ionic compound. So let's use something like magnesium acetate. Let's go through this naming here. So this is an ionic compound. So that means that the magnesium and the acetate are ions. So what's the charge of a magnesium ion? Anybody have anything there that they can? I'm getting your sheets laminated for you. Your constant sheets. I'll get those for you eventually. Here, let me pull down the periodic table. So here's magnesium, 2 plus. Okay. So magnesium is 2 plus. Acetate is C2H3O2 with a -1 charge. So what's the formula when those two combine? How many magnesiums? 1. How many acetates? 2. Okay. Now, if that's a solid, when I put that into water, is that going to be a strong electrolyte or a weak electrolyte? Strong, why? How do you know, other than me telling you that it's a strong electrolyte, how do you know that it's going to be a strong electrolyte? Acetate, right. Because of the acetate ion. So that means that we have a one-way yield symbol, one-way arrow, and we have almost entirely just ions. One-way yield symbol, so we have mainly products. Okay? Now for a weak electrolyte, let's use something like silver sulfate. Oh, pardon me, silver sulfide. Let's use silver sulfide. Silver is a +1. The sulfide is a 2-, so what's the formula? Ag, how many? 2. How many S's? Just the 1, yeah. Now, how can you tell that this is a weak electrolyte? Right, it doesn't have group 1. Nitrate, acetate, ammonium. Is there another one? That's it, right? Get you remember? So since it doesn't have one of those 4, we do an equilibrium symbol. So there's the equilibrium symbol, which means that the reaction is going both ways. We're still going to break it up into ions because it's still an electrolyte. But more than likely, we're going to have more reactant than product. So this one's going to be almost entirely product. Or reactant, pardon me. Almost entirely reactant. All right. Anybody have any questions?